Right, so review. Where are we? We wanted to prove Dirichlet's theorem, sum over primes congruent to A mod Q, 1 over P diverges. This is implied by the fact that L1 chi Q, which is the real one, is non-zero. This is implied by the fact, okay, so now let's specialize to the case Q is a prime that's 3 mod 4, by the class number formula, which is that L1 chi actually equals, what is it, pi over root Q times the class number of Q. And even this has to be adjusted a little for a couple of, depending on the size of the unit group. But anyway, so this formula is what we're working up to. And again, I want to follow a scenic route to get there. So let's go all the way to, so we saw what the class number is, and we saw that the class number is finite, and we saw fundamental domain for the action. We saw fundamental domain for the action of SL2Z on, or PSL2Z on the upper half plane. Let's give more structure to the upper half plane. Okay, so more structure, which will also work towards our goal of talking about homogeneous dynamics and such things. See this? Okay, yeah, I'm leaving an area here. So let's give that extra structure. So you see, in the 19th century, people used to think of manifolds. So what was a manifold? Manifold meant a surface. You know, it was something like you have some embedding, you have some shape, you have some embedding, I don't know, iota of, let's say, R2 into R3 or something. Okay, so for every point xy, I give you a point z, and that's my sort of, and the image of the, the graph of this is a surface. Mm-hmm. And it's really Riemann that initiated our more, so this is 19th century, our modern understanding of how we should do geometry, in particular manifold. So what is it? What is a manifold? Yeah, it's an abstract concept. It's an abstract concept where we have what's really fundamental about these things is that we have charts. We have charts and atlases. Charts which are grouped together into atlases. So we have an atlas of charts where locally in a neighborhood of any point, we have a map, and that map is to some Rn. And now it doesn't matter. So in other words, this point X maybe goes to the origin. Let me call it Z, or later goes to the origin. And if we have two charts that overlap, now we get a map from Rn to Rn, and we can speak about being, topological manifold, smooth manifold, depending on whether the map that goes back and forward, so the map that goes, the inverse map and the forward map, now it gives you a map from Rn to Rn, and whether these maps are everywhere, differentiable, yeah, whatever class, whatever category you want to work in. So this idea is really due to Riemann, and it's also why he could work in arbitrary dimensions. Now, Nash's embedding theorem says that actually any abstract manifold can in fact be embedded into some much higher dimensional Euclidean space. Okay, so Nash says that the 19th century guys were okay, but anyway, I just want to mention the Nash embedding theorem here.
This sort of is everything, right?
Right, right. That
the intuition is enough, right? It's in a high enough dimensional Euclidean space you could fit things.
Right.
I've seen it called wicking embedding or smooth manifolds.
Right, and Nash got the whittled down how much differentiability.
Okay, and so that's more general.
Right.
Manifolds. Okay. Or topological manifolds.
I don't remember. I think you need two derivatives.
Okay.
But don't quote me on that.
Okay.
Maybe somebody can Google it. Okay, so the point is, so we have this structure, and then Riemann's idea is how are you supposed to do geometry on the structure. What does it mean to do geometry? Well, geometry means measuring distances. And to measure the distance between 2 points, we need a curve from 2 points. And how do you measure the length of a curve? The length of a curve, if I have some curve gamma, let's say gamma is a curve from some point P to Q. Gamma, let's say, takes P, I'll write it like this, takes P to Q.
Hyperbolic stuff?
Well, we're working up to that. But just for general, general knowledge, let's say gamma is really a function from 0, 1 into your space with gamma of 0 equal to P and gamma of, so this is gamma of 0 and this is gamma of 1. Then the length should be the integral from 0 to 1 of the little arc lengths. And the little arc lengths, if gamma is differentiable, is the derivative of gamma with respect to t, that length, dt.
It's really a complex analysis way of looking at it, right?
This is also what you do in complex analysis, but it's a general analysis way of looking at it, I would say, or a general geometry way. I mean, this is what geometry is about, measuring distances. And so to measure a distance, you have to measure a length, which means you have to first measure a length locally. And this really is the square root of, gamma of t squared, which I'll write as q of gamma of t. So q, the point is what Riemann understood, Riemann's main idea here, Riemann, well, it's called a Riemannian geometry or a Romanian structure. Romanian structure is to locally measure lengths, locally measure lengths via some quadratic form, via local quadratic form.
Because x could be anything,
Could be anything,
right?
could be anything, right?
It's defining what this would be.
Exactly.
Square root of q. Okay.
Exactly, yeah. So x is some quadratic form. We're probably thinking of the Euclidean one, which is what I drew here, but there's no reason to take the Euclidean. So first we have to say what it locally means. Okay, so if I have a curve, so let me draw another picture. So here's x again. I'm drawing it like a surface, but there's an abstract manifold. If I have some curve gamma that passes through, so let's say gamma goes from -1 to 1 into x, and gamma of 0 is our point z. Okay, so this is the center point. Well, then I have a chart. I have a local chart to Rn, where z goes to the origin, and now I have some image of gamma under this chart. I'll still write gamma for that. Okay, and here's the image of z. If gamma is differentiable, then it makes sense to define, it has this derivative at 0. So this is the vector gamma prime at 0, right? It's just a one direction derivative. And the key idea is we'll say curves through z, curves smooth meaning at least once continuous differentiable. Let's say C1 curves through z are equivalent curves, let's say gamma 1, gamma 2 are equivalent if and only if these derivatives are actually equal. So if I have two different curves and they pass through, so here's gamma 1 on top and gamma 2 on bottom, and they pass through the origin with exactly the same tangent vector, not just the same direction, but the same vector exactly, then I'll say those curves are equivalent.
Is this with a fixed map from our manifold Rn or for any map from our manifold?
Okay, so in other words, if I have a different chart around z,
Yes,
what happens to?
Or I guess, yeah, the same region, but with a different.
No, so first,
charts, right?
to fix a manifold means to fix all the charts.
Okay.
If you give me a manifold, that means you've given me all these charts.
Right, so you made a.
But now I have a choice about the Riemannian structure.
Hmm.
With these charts, now I can say, okay, I can differentiate here. I have some derivatives. If those derivatives are equal, then I say that these curves are identified. And then the tangent space, this is the tangent space to x at z is the set of all such curves, the set of all curves from -1 to x, whose value at 0 is equal to z, up to this equivalence. Can you see?
Oh, okay.
Okay, so these, in other words, when what do we think of as the tangent space? You know, again, I'm drawing this surface version. If I have some point z, then the tangent space is some space that's tangent to x at z. And so what does that mean? Well, look at all the possible directions that you can pass through z at all possible speeds, and that's all of these tangent vectors. Let's call them eta or something. And that gives me a bunch of these derivatives. And I just want the values of the derivatives and not the curves that gave me that derivative. So that's curves up to equivalence. So that's this tangent space structure.
Why is this natural to think about? I guess you.
How else should you define, what does it mean to define a derivative, right? You're moving along x through some point.
I feel like it got a little lost, right? So if you're in an arbitrary manifold, you're
Yes.
saying that you go and you take a chart, and then you look at all the curves going to the point.
Yeah.
Then you see the value of the derivative through 0.
Yes.
And then if they match, you group them together.
So if you have two curves, in other words, let me try to draw a better picture of what that would look like. If I have one curve that does that and another curve that does that, that's this gamma 1, gamma 2, those are different curves. But right around 0, hopefully the way I've drawn it is they both have the same,
Right.
exactly the same derivative. And what we care about is that derivative. That's what a tangent vector in the unit tangent, in the tangent space at z is. So I want some version of, you know, if you're thinking of a surface and you want a tangent plane, well, this states, and you want a tangent plane to it, to a point, how do I define this? So I can define this as you look at all curves through here, and I just want to know what direction it's going in at what speed. So that's exactly what we accomplished with this definition. Does that make sense? Ask if not.
Maybe another way to think about it is like the same explanation, but slightly different. Is the tangent plane should be like the directions you can go from that point.
Exactly.
And what is the direction? It's the derivative. What was the direction of a curve? It's the derivative.
The direction is a derivative. Like what I'm confused about, I guess, is if you have a tangent plane, there are like many directions you could go on the plane.
Yeah. So here's a non-equivalent curve that has its own derivative. So we have this point, all of these different things.
But then you're like taking TZ.
Maybe how I'm drawing it is I'm drawing it here to give you the intuition of what it's supposed to be. But formally, it's just this definition.
Right. Yeah,
So
I'm just a little confused about how we're grouping things, I guess, right? So you're saying that the set of equivalence classes
Yes.
is TZ.
Yes.
Okay, perfect. Yeah, that was confusing me because I was
Yes.
like, oh, but you could definitely have different derivatives, right?
Yes.
In which case, you have different derivatives, how could you call that a derivative? And then what you're saying here is your derivative is
That is this.
equivalence classes
Yes.
of curves with each their own derivative.
Exactly.
Okay, I think yeah, sorry about that.
Okay. So each has their own derivative.
Dimensional vector space, which is important.
Okay. So that's the tangent space, and the tangent bundle. The tangent bundle is just the union over all of these. And then you have to worry about what happens on overlaps. That's also what makes gives you this structure. And now, so now that we have this notion of what the tangent, so I said locally, the Riemannian structure is locally to measure lengths via quadratic form.
Also, by overlap here, you mean that, oh, it's possible that one same curve for different points, right?
Right,
Might be in like. Right?
exactly,
Okay.
exactly. So this same curve passes through this region and things should vary nicely.
Okay.
Again, I just wanted, this is just a crash course in things. I don't want to get into there's a whole
Yeah,
course
yeah.
that we should be doing on Riemannian geometry. I just want to motivate some of these definitions
I just
by,
don't want to be lost.
Sure.
Yeah,
by putting them in the perspective of where they are.
that's good.
So now we know this tangent space. So what's a Riemannian structure? So again, Riemannian structure is a quadratic form at each tangent space, a quadratic form QZ on the tangent vectors, quadratic form on these tangent vectors.
Actually,
Exactly. So that we can define, so that length and then length of a curve will be, as before, an integral of the square root of the quadratic form of these tangent vectors. So this is now some tangent vector integrated with this square root t.
oh, yes.
Okay, at each point, it's moving through these different terms. Okay, so in the case of let's do this for the upper half.
I guess like it makes sense for it to be a quadratic form, right? Because like original distance is sort of like, I say, like in R2, right? It's sort of like you take squares, the sum of squares.
Yep, sum of
right?
squares, sum of squares. Okay, so maybe before hyperbolic space, for x equal to R2, the charts are all the identity. And the quadratic form at every point for all z, the quadratic form, so the tangent space to any point in X is also R2. And a typical tangent vector here is commonly denoted dx dy. So if R2, here's R2, and here's a point Z, and a curve passes, well, I can just say, here's the tangent vector dx dy. Or you can call it eta if we like. And then the quadratic form of dx dy is dx squared plus dy squared. And that's what people call dz squared. It's just Euclidean quadratic form. It actually doesn't depend on the value of z.
Right.
Okay, so for the upper half plane, what are our charts? So here's the upper half plane. What's my chart around z?
This is probably fine.
The identity map. Yeah, exactly. So the charts are the identity. Charts are the identity to, well, R2 or C, depending on how we should probably think about it, C. And so there's no question about overlaps. It has all the structure. And what's the unit tangent? What's the tangent space to a point?
Same thing.
Yeah, also C, also R2 or C. We can also think about it as C, because we can have any tangent vector in any direction.
Right.
Okay. So now we need to give a structure, a quadratic form, and the hyperbolic structure. The reason this is called the hyperbolic upper half plane is that the hyperbolic structure, the one with constant negative curvature, is to give the quadratic form Q at Z of eta, which you can write as dx dy, is the Euclidean length divided by the imaginary part of Z.
And is this sort of like an arbitrary choice? Could you be like, oh, let's just put some random quadratic form and see what kind of geometry it gives us?
You can absolutely put a random quadratic form and see what kind of geometry that gives us. And that's what Riemannian geometry is. It's the study of what geometry, what such geometries are, to which extent is there equivalence, what happens to various flows, on such a geometry. This is the one that gives us hyperbolic space.
Right.
Okay, so just to be really concrete, well, I think this is already concrete, but yeah, okay. So this is how we're going to measure lengths, and then there's a very useful. We will be concrete in a second. There's a very useful subspace here, which is the unit tangent bundle. So now that we have a Riemannian structure, we can say, what is the unit tangent bundle? So the unit tangent bundle, it's the set of all points z and tangent vectors eta in the tangent bundle, such that the length of eta as measured at z by this quadratic form is 1. Okay, so again, we have now a point z and a unit tangent vector eta. We have a way of measuring lengths of each of those, and the unit tangent bundle is the set of length 1 tangent vectors from z. And so my question is, what does this look like? Have I drawn this correctly?
Attaching a circle at each point.
We're attaching a circle at each point. What is the
Circles can be a little weird.
so z, length of z is the Euclidean length.
Okay.
As a complex, I'm treating eta as a complex number. So what does it mean? What does this actually look like? If eta over the imaginary part of z, I'll call that y, is equal to 1, then the length of eta is exactly equal to the height of z. So in fact, this is the set of unit tangent vectors around z. And if z was here, then this would be the set of unit tangent vectors around z.
Horocycle looking things, right?
Yes, but we shouldn't think about, so this circle isn't taking place in H itself. It's taking place in the unit tangent bundle, in the unit tangent space to z. So yes, the way I've drawn it, it looks like a horocycle, but it's
Okay.
I see how it would be easy to confuse the two, since they're the same, exactly the same picture, but the pictures are what's misleading.
Incompatible in a sense.
Right, right. So if you're up high, in other words, if you're somewhere up here, then a unit tangent vector is very long, Euclidean long, right? And if you're down low, then a unit tangent vector is much shorter. These have the same length. These tangent vectors have the same length. Have the same length in hyperbolic space.
In a sense, you can't go below the boundary, and like to get close to the stuff up high, you have to stretch pretty long, right?
Exactly, exactly. So if you're moving at unit speed, in 1 second, you wind up over here. Although that's not exactly right, because you have to move along geodesics. We'll get to that in a second. And here you move a much smaller Euclidean distance.
Right.
Okay, so let's get to geodesics. Sorry, did you have a question?
Nope.
Okay. So let's get to geodesics. So what is a geodesic? We already said if we have 2 points, let's say P and Q, we can consider all the curves, gamma. So look at all curves, gamma, that take P to Q, and compute their lengths. And the distance d, let's call it d, from P to Q is the minimum over all such, C1 curves from P to Q of the length of the curve.
Are you guaranteed for it to be a minimum, or do you have to like assume it's an infimum?
Yeah. So first we have to do an infimum. You're absolutely right.
I'm just wondering.
general?
some compact
No, in
thing
general,
like-
yeah, in general, it's an infimum. So now we have a distance, and then a geodesic from P to Q is a curve that minimizes with the length of the curve being exactly the distance.
In general, is it possible for you not to have a minimum?
Yes, take R2, take away the origin, and then just take like -1 and
Yeah.
1. There's no geodesic, there's no.
Okay, yeah.
It's better.
Okay, that makes sense.
Yep.
Okay.
I want,
Complete manifold when geodesic or length minimizing geodesics exists.
Exactly.
I want to ask if we can find a chart, like a better chart maybe, where it actually respects distances.
A better what?
A better way of going from
Like an
upper half,
isometry or something?
yeah, from the upper half plane to a copy of R squared.
That respects distances? You mean that respects Euclidean distances?
Yes, I'm just saying that now we have naively, I guess, put the upper half plane and corresponding to R2.
Uh-huh.
In x comma y goes to x
Sure.
comma y.
Yep.
But maybe if we find a fancier way of sending our upper half plane to S surface, a two-dimensional surface, maybe it can actually preserve the Euclidean distance on the
Ah.
right.
So you're asking, so we've given a geometry to the upper half plane, right?
Isn't that like a
Yes.
saddle or something? Like,
Locally, it's a saddle, and there's a theorem that there is no immersion of R2 even into of the hyperbolic plane even into R3. So not only can you not put it in R2, you can't even put it in R3.
Because it seems like the arrows that you've drawn, it seems as if the closer to the origin, like we can think of it as going like this. Like, but I mean, that's not precise, right?
It's not precise, and it's also these pictures give a misleading notion of what it would feel like to be an ant on the surface. So if you're an ant standing in hyperbolic space, locally at a chart, it's exactly what Andre said. That so this is, I'm sure, not evident from what's drawn here, but so how much time do I want to spend going into hyperbolic geometry versus not? If you walk around, so here's what's really going on. If you put a stake in the ground and you walk around that stake at a fixed distance, if you're in Euclidean space, let's say that distance is epsilon. If you're in Euclidean space, then you walk around a distance of 2 pi epsilon. If you're on something that locally looks like a spherical cap, then when you put your stake in the ground and you pull your string taut and you walk around a distance, epsilon ball, that distance epsilon ball is actually less than 2 pi epsilon, because 2 pi epsilon would be out here in space. In fact, that's how one could theoretically at least measure the curvature of the Earth for the flat earthers.
Yeah.
But anyway, you'd have to go pretty far out and measure extremely precisely and so on. Okay, so this is circumference equals 2 pi epsilon. This is circumference if you're on a sphere, then the circumference is equal to is less than 2 pi epsilon. Now, how could the circumference be more than 2 pi epsilon? If you live on a saddle, if you're secretly locally on a saddle where one direction looks, well, one direction is concave, one direction is convex, then if you go a distance 2 pi epsilon, if you go a distance epsilon away from that point, staying in the geometry, you actually have to walk more than 2 pi. So this is the circumference being greater than 2 pi.
This is where hyperbolic comes from, right? Because the cross sections of this are hyperbolic. The saddle.
Right. So you can take the sectional curvatures, which means when you take sections through the space, you get a curvature. Curvature means the 1 over the radius of the circle that best approximates that curve locally. So you can take through any point, you can take the largest and the smallest curvatures, and when you multiply those two, that's Gaussian curvature. And when that product is negative, so here you have in every direction you have positive curvature. Here in every direction you have 0 curvature. And when you take the product here, one curvature is positive, one curvature is negative. And so this is constant sectional negative curvature. Okay. So this is so locally the hyperbolic plane actually looks like this. But everywhere it doesn't look like that. It doesn't look like that it's not a Pringles chip. It's a Pringles chip at every single possible place.
Right.
So the second you move a little bit over, again, you have another saddle
Another one,
here. And over here, you have another saddle.
Right? It's not like we cannot put it on R3. So
We can't even embed it in our
yeah.
three.
Oh, I see.
Very sad.
Yeah. And people attempt to do local crochets that, that start looking. You can even do this with triangles. If you take 3 triangles at a vertex, and you try to follow that rule all the way around, you immediately get a tetrahedron. Right?
I think that's one.
Yeah. If you take 4 triangles, you get an octahedron. If you take 5 triangles and you follow that rule all the way around, you get an icosahedron. 6 triangles now meet at a flat edge. So 6 triangles tile the plane, hexagons. 7 triangles, now you have to, some of them have to pop up and some of them have to go down to fit around a vertex. And if you continue that 7 triangles as far out as you can, if you have a whole mess of triangles and they stick together really nicely, you can get a feel for hyperbolic space that way. Can you sort of imagine what I have in mind?
I think so, but that seems very symmetrical in all directions. The hyperbolic plane seems that up is easier to go than down.
No, it's it's a homogeneous space. Every point looks exactly like every other space. It's just that we're viewing it through the lens of Euclidean. We're sort of, it's like you're saying, if I draw a sphere.
Going up is easier, right? That's what
In the Euclidean sense.
of course less.
Euclidean going up costs less, but if you're an ant in hyperbolic space, they all look exactly the same. This point looks exactly the same as that point.
Okay, I think I would buy it, but it's a bad coordinate system if you're an ant.
If you're an ant, then you wouldn't use this coordinate system.
Yeah.
You would just see whatever you see around you.
Yeah.
But it's just like if you look at Escher circle limits, right? If you have like angels and devils, and you have an angel here and a devil here, and then you have a little angel there and a little devil here. This angel is exactly the same size as this one.
Right.
Just like when I drew a sphere. This isn't a sphere. I can't draw a sphere. I'm drawing in 2 space.
Yeah.
But we're so familiar with this distortion that we don't even bother to, it doesn't even faze us. Whereas this distortion is less familiar.
Yeah, once the ant walks over from one location to the other, the A's look the same.
They look exactly the same. Okay, so this is a distorted image because I'm projecting it to R2 or to the unit circle. I'm also projecting this to R2, but this we don't have any problem with because we have so much experience. This is distorted in exactly the same way, but the ant looks, every point looks the same. And same thing here in a hyperbolic space, every point looks the same to an ant. We're viewing it from this distorted image of the upper half plane.
Then later, we're gonna see like non-homogeneous kind of stuff going on, right? Like when you act by a group and then all of a sudden you have to redefine your charts.
Right, when we take a quotient,
Right.
we still locally, but it's the size of the charts that we have to
Right.
deal with. Okay, so where were we? So in general, a geodesic is, if it exists, a length minimizing curve. And so let's see what the geodesics are. So who are the geodesics? Who are the geodesics?
Relative to hyperbolic distance.
Yes, in H with the Romanian structure that we just discussed. Okay, so, well, you guys all know the answer, but how do you prove that those are the only ones?
Look at Einstein reward.
Yeah, you first do the vertical ones.
Okay, so one is easy, which is the vertical one.
The vertical
Easy
centered at
case.
the y-axis, right? Sort of the imaginary axis.
It doesn't matter where they're centeredness. I mean, as long as they're vertically, if I have a point Z and a point W with the same imaginary part. So I can take any curve that sends Z to W, and I can look at the length of that curve. The length of that curve is again the integral from 0 to 1. The derivative, now so it's the square root of, if I write my curve gamma, if I write gamma as x of t comma y of t, then what's the locally at any point t, what's the metric? It's x dot of t squared plus y dot of t squared. In other words, the Euclidean, what would be the Euclidean length divided by y of t squared. That's exactly the, I gave the quadratic form in its square root form. The square root of the quadratic form is this. It's the
Yeah.
Euclidean length
Yeah.
It's the Euclidean length divided by the imaginary part squared.
And now, yeah, this is bigger than if we don't write x prime.
Exactly, exactly. The best is if x prime is 0. So this is at least the integral where x prime is 0, since this is a positive quantity. So it's the derivative in y divided by y dt. If the derivative is, I mean, I can put absolute values here, I guess. Square root of the square. Y is already positive. This is also larger than if I put no absolute values. In other words, the first one was just to drop the x. The second one is to say, well, the absolute value function is always greater than the function itself. And so the straight curve that doesn't backtrack is a geodesic. So vertical lines are geodesics if z and w have the same imaginary part. And what about if not?
If not, find the fractional linear transformation.
Yeah, then we actually have to do something. And the thing that we have to do is to observe. So in order to do that calculation, bless you, we should observe, bless you, that G, which is SL2R, our favorite group, PSL, whatever. We can extend the action of G on H extends to an action on the tangent bundle, in fact, and in particular on the unit tangent bundle. How? So if I have a point, so I want to know what the differentiation at Z of G. So G is some G in G is some ABCD. What is the differentiation? In other words, I have Z and I move Z to some G of Z. And I had some curve that went through Z. And then so this was gamma. So what happens to gamma, G moving all of gamma? So the derivative used to be gamma prime of 0 was my eta. So now I have a point in a tangent vector. And now I want to know what this new tangent vector is. Well, it's just the chain rule. It's just the chain rule. So the derivative G gamma prime is G prime of gamma times gamma prime. Gamma prime at 0, so this is at 0. At 0, gamma prime at 0 was eta. And what is G prime at gamma of 0? Gamma of 0 is Z. And now I need to know what G prime of Z is. Well, G of Z is AZ plus B over CZ plus D. And the derivative is, what is it? Bottom times through the top minus top times through to the bottom, all over bottom squared. CZ plus D squared, not norm squared. The top simplifies, AD minus BC. That's why we're in SL2 and not GL2, so we don't have to carry determinants around. So I get 1 over CZ plus D squared.
Is the theory still fine if we carry the determinants around?
Yes, but then instead of having, so the determinant will be here, and then I have to do something else in a minute that you'll see where the imaginary part is no longer the imaginary part over CZ plus D norm squared. It becomes determinant over CZ plus D norm squared.
I guess what I wonder is, could things break, right? Some theorems apply specifically to PSL2 and not to GL.
No, because the action of the center is always trivial. This fractional linear. So whatever it is, it's going to wash out in the end. Okay. So what is G of Z eta? Well, it's the fractional linear action, AZ plus B over CZ plus D. And what is the action on the tangent vector? It's exactly what we said here. It's the tangent vector, whatever it was, divided by CZ plus D squared. Okay, this is how G, all of G,
Interpreting, right, these like fractional linear transformations, but yeah.
yeah, exactly from this computation. It's just taking the original unit tangent vector. The new tangent vector will be the original tangent vector divided by CZ plus D squared as a complex number. So that's G of eta. That's how G acts on tangent vectors.
So do we have to check that the length of eta over CZ plus D squared is still 1?
Okay, so is this an isometry?
Well, I guess we have to check that, otherwise we don't know that G acts.
That's right. That's right. It acts on the tangent bundle. Does it act on the tangent bundle? Unit tangent. Is this an isometry? Right. So this is what's in question. Is this an isometry? And well, let's measure the length. So the length, so we assume that Z eta was in the unit tangent bundle to Z at H. Actually, this has nothing to do with unit, just whatever the length was. Are we keeping lengths the same? But since we're restricting to units.
That's pretty much a consequence of complex analysis, right? Like the automorphisms of the upper half plane.
This goes a little bit beyond complex analysis because we're actually looking at these flow. Well, we're going to be looking at the flows in a second, but we're looking at tangent spaces. So this is now, the unit tangent bundle is somehow a three-dimensional object. So we're not in complex analysis anymore. Right. So what does this mean? It means that the length of eta as measured by Z is 1. But what is that? It's the Euclidean length of eta as a complex number divided by the imaginary part of Z. Okay, what about the length of G eta, which is this thing, as measured by GZ? Well, that's the Euclidean length, in other words, eta over CZ plus D squared. So this is a complex number. I want to take its Euclidean length and I divide by the imaginary part at the new point.
And that we already computed.
That we already computed. And this is where if you weren't doing PSL, you would get another factor of the determinant here and here. They would cancel. The imaginary part.
So follows through.
Exactly. Exactly. So I get eta over CZ plus D squared. I'm just rewriting the numerator. And the denominator is the imaginary part of GZ, which is the imaginary part of Z, times absolute value of CZ plus D squared. So here there's an absolute value. Here there isn't. It's just CZ plus D squared as a complex number. It can change the argument. But we're taking Euclidean length, so that puts the absolute values, and these exactly cancel. Okay, so this has nothing to do with being unit vectors. Whatever the original length was, the new length is the same. And in particular, if the original length was 1, then the new length is also 1.
Does this like validate our choice of like group and distance?
Yes.
Right, like they're compatible with each other, so like.
Yes, exactly.
Okay.
Exactly.
If this didn't work out, then maybe something nasty would happen.
Right. So this is a local isometry. Not only, so why does it preserve all distances? Because it preserves all local distances, and a general distance is an integral of local distances. So it preserves distances locally, which means it preserves them globally. So far, so good. Okay, so this action of G is indeed an action on the unit tangent vector. So what do we do for 2 points?
Okay, so this is the same, for example, maybe this is stronger actually, but at least it feels the same as if I take the integral over G gamma, then it's just a change of variable with determinant 1, and it's the same as the length of the curve gamma. So
If I take the integral of
I'm
G
just
gamma,
saying L of gamma is the same as L of G gamma.
yes,
And this is
Yes.
achieved through a change of values for determinant 1, but you've done something faster. You've seen locally.
well, no, so y is the length of any curve. So here's gamma, and then G gamma takes it somewhere. Why is the length of G gamma the same as length of gamma? Well, what is the length of G gamma? It's the integral of the square root of the length of G, well, the local length of G gamma, in other words, G gamma prime, as measured at G gamma dt. And for every value of t, it's not just that the integrals equal, but the integrand itself is equal. This thing locally is also equal to the length of gamma prime as measured at gamma of t. This is the length measured at the point wherever it was originally.
After this computation, I guess this computation was the proof.
This computation was the proof that they're the same everywhere locally, which means that when you integrate them, of course, they're going to be the same. Okay. Something you don't like?
No, I'm just wondering, like, why?
I thought this was achieved through a change of variables and the determinant was one, but I was wrong. I mean, they're literally the same thing.
They're literally the same
They're not
thing.
the
That's
same
exactly what we
variable.
computed here.
Oh, that was the conclusion.
Yeah.
Okay.
Okay. So if we have 2 points, Z and W, what do we do? Yeah, what's that change of variables? How do we find it? How do we find an action? Sorry, say it again.
One of them anywhere I want.
You can put one of them anywhere you want. That's right. You can put one of them at I, if you like. What happens? Yeah, where's your freedom to put the other one? The trick, and this is a theorem of the ancient Greek Apollonius. So Apollonius says that there's a unique circle that passes through Z and W and is orthogonal to the boundary.
I wonder what this might be.
Right? It's a slight variation on some of the other Apollonian theorems. There's a unique circle that does this, and whatever these points are, alpha and beta. So here's the much easier exercise. There exists a map, there exists a G in G, so that G of alpha is 0 and G of beta is infinity. So we can always map alpha to 0, beta to infinity. Okay, then we have to know that circles and lines go to circles and lines under fractional linear transformations. So this circle has to go to a circle from 0 to infinity. Of course, Z was somewhere here. W was somewhere there. We already know that this is the geodesic. And we know what its distance is, which means we know what this geodesic. We know that this is the geodesic, this curve, which is the image of this line
Once we
going
see that.
backwards.
And the G of alpha, G of beta thing is just a matter of flexibility with your variables, right? You have
Yes. Yeah, there are two. In fact, we can go one step further. We can see 2G SL2R is a 3-dimensional manifold. Right? You have 3 degrees of freedom. You can choose like A, B, and D, and then C is determined or something.
right.
Not exactly. There's charts there as well.
The geodesics don't change form if they just go right and left, right? They are the same. If I have W plus N and Z plus N, they'll have the same exact.
Because so the translation is invariant because 1x01 is an element of G.
Okay,
Like
so
the
we can,
imaginary
without loss
function.
of generality, assume that W is I, or, okay, actually, I'm right, the W is on the imaginary.
Is on the imaginary. We can assume that.
Okay, and then you can actually find where you should send Z, where you can send Z.
But in the process of sending Z, you have to fix W.
Yeah, well, what I'm saying is that instead of solving the problem, more they can solve the problem if W is I. And if I find that geodesic when W is, okay, not I, but I guess of the imaginary part.
Yeah. So you're saying you can definitely move W to the imaginary part.
Yeah, let's assume. Yeah, and then I think we can find that Z that sends Z somewhere on the line.
We can, but how?
I saw the.
What we want to do is understand the stabilizer of W, which will be some conjugate of K, and K will be the rotation. And so there's some rotation that moves Z either here or here, wherever you want it to be,
You have to move the simultaneously, that I did, yeah, of course.
while fixing W.
Right, right.
Once you find that rotation, then you can just compose with the thing that W back where it belongs.
Sure,
If you want.
sure. But I think it's much easier just to write down a fractional linear transformation like this.
Numerator vanish, denominator vanish, and then,
Yep.
When we do that fractional linear transformation that takes alpha to 0, beta to infinity, why must W and Z end up on the line?
So what I said is, this is a little calculation that you can check, that circles and lines go to circles and lines under the fractional linear maps.
Oh, and then those are the only, okay, that is the only line that connects 0 to infinity.
So, and there's
Okay.
one circle that connects 0 to infinity, which is the straight line.
Oh, yeah.
I mean,
And so Z goes-
geodesics are unique in a sense, right?
Exactly.
And it's like,
Are we taking upper half plane to be the open set, or are we taking its closure?
So we can extend the action to the boundary.
Yeah.
We talked about that.
No, not yet.
Oh, we didn't talk about extending it to the boundary as projective, as P1.
Oh, we did talk about P1 for, oh, that was like in Friday's lecture when things got.
Oh, is that right? I thought we talked about it. Anyway, we can look back. Anyway, there's an extension to T1.
I mean, like
There's an extension to
the
the,
fractional
boundary.
linear map still makes sense,
exactly.
right?
And then we'll always take the boundary to the boundary, well,
Yep,
boundary.
yep,
Okay.
Yep. exactly. Okay. Good. Did I want to say anything else before getting to what I really am trying to get to is the Laplacian and the Eisenstein series. But this is a good, oh yeah, let's talk about the various kinds of transformations. Well, we've sort of been talking about, so given that we know what the geodesics are, now we can define geodesic flow. So given, or in general, we can always define a geodesic flow. Let's say, given a point in any tangent, but in particular, let's say driving at speed 1, the unit tangent bundle, we can define the geodesic flow. Geodesic flow, some people call this VT, which is you follow, you have Z and you have eta, and you follow the geodesic that's locally in the direction of eta for a time t,
And this is
for a
like
distance t.
uniquely determines the geodesic already.
It uniquely determines geodesic already, again by Apollonius. Apollonius is everywhere here because eta gives us a line, the boundary gives us a line, and Z gives us a point. So there's a unique semicircle tangent to this line at this point and orthogonal to the boundary, which you can construct with straight line compass. And as we move a hyperbolic distance t along here, this is hyperbolic distance t, we get a new point and a new tangent vector. Under this identification, so here's Gelfand was sort of, so people did all this geometry long before algebra got involved. But Gelfand observed, Gelfand and Flamin in this case, but in many, Gelfand sort of systematically took things that people were doing in geometry and tried to reinterpret them algebraically, representation theory, to put representation theory front and center. So Gelfand reinterprets this action algebraically. How? He claims that the geodesic, under the identification, right? We need to do the identification. So identify.
Stabilizing and all that.
Yes, exactly. G we can identify not only can we identify G mod K with the upper half plane, we can identify G itself with the unit tangent bundle. Okay, why is that? What's the identification? If we take a point G and we map it to the action of G on the unit tangent point, let's call it I up or II, if you like. Okay, so I up is my sort of central point, although any point will do.
You have to trivial stabilizer.
Well, that's exactly what we're about to show. We're about to show that this action is transitive and that the stabilizer is trivial.
Right.
In which case we get this identification in the same way that we had this identification. Okay, so again, this means AI plus B over CI plus D, comma, up is I over CZ plus D squared. Okay, so why can we get any point here and any complex number here by varying A, B, C, D subject to AD minus BC equals 1? That's our task. And the identification is very simple. Let G equal, so as we saw last time, we can decompose things as N, A. Since I'm in SL2, now I have to put square roots instead of allowing myself to write 1 and Y.
CZ plus D should be CI plus D.
CI plus D.
Yeah.
Thank you. Z is I, thanks. And then I have a K, a compact element. Okay, so this I can write as NX AY K theta. And let's see what it does to each of the terms exactly. So G of I comma up, then we already know that it takes I to, I mean, we can do it again, but K is the stabilizer of I, so K does nothing to I. Okay, let's write this as NX AY K theta I, comma, something. K does nothing to I. AY shifts I up by Y. This is YI. And this whole thing, and then this whole thing is X plus I. Okay, so we can move, we already knew this. We can move to anybody. What's happening on this side? What is CZ plus D? CI plus D squared with an I here. So we have to work that out from G. What is G? So if I multiply these two together, let's see, the diagonal, this is upper triangular, so the diagonal stays, and it stays upper triangular. And this is something, but actually it doesn't actually matter what that something is. That something is, what is it, X over root Y or something, but it doesn't actually matter what that is, because all I need to know is what the bottom two entries are. So let's work out what these bottom two entries are. So I have 0 sine theta minus sine theta cosine, what is it? Minus sine theta over root Y there. And then cosine theta over root Y here. Right?
What are we trying to prove in that?
I'm just multiplying out what G is. I want to apply the formula I over
Oh,
CI plus D parentheses squared.
oh, okay.
Okay, so it's CI plus D
Yeah, like 1 over Y is something.
parentheses squared.
Oh, but that's a literal square.
That's a literal square. It's not an absolute value square. It's a literal square. So
K theta fixes I. It is, oh, okay, K theta is the stabilizer.
K theta is the stabilizer.
Okay, I see.
So what happens when we square this? Well, the root Y comes out with a 1 over Y. So I just get YI. So this whole thing, if I simplify things a little bit, I get YI divided by cosine theta, I guess, minus I sine theta in the denominator. In other words, I'm dividing by e to the I theta, which means I could multiply by e to the plus I theta. Which means I'm taking my unit vector, my vector up, I'm scaling it so that it has the right length, so it has the same length, so it remains to be length 1, hyperbolic length 1 relative to the imaginary part, and then I'm rotating it by an arbitrary angle. So in other words, the action, if I had some point z eta, well, let's start with, I'm sorry, squared, thank you,
Oh, yeah.
2 theta.
It's still under.
The angle is still arbitrary, but you're absolutely right, it doubles the angle.
Right.
It doubles the angle. So if I start with I up, and I move, G moves me to some GZ, well, what's the angle? The angle without the theta is wherever, is just this translation. In other words, without the theta, the angle would be IY, where Y is exactly this distance. This distance is that distance. And now I get to rotate by something. So I get an arbitrary vector in the unit tangent bundle, in the unit tangent space to GZ. This is my last degree of freedom in the unit tangent bundle, not in the tangent bundle. I can't change the magnitude. Nick, I lost you.
Okay, so I get the y there, I get an I, and then
So I just get a cosine. Where am I? Here. I get a cosine minus I sine.
Yep.
So that's e to the I theta with e to the minus I theta.
which then turns into minus 2i theta, which then from the numerator I get e to the 2i theta, and then I also have that for y factor squared.
Uh-huh.
The I stays in the numerator. Okay.
Yep.
And this becomes y. Okay.
Great.
I'm on board. I've got it all.
All right. So this action is indeed transitive. It takes any point to any other point. So action is transitive.
Oh, the last thing you're saying is, okay, you can choose your theta to line up.
Yes, exactly. If I want to get to any vector, any tangent vector to this point, GZ, which is x plus IY,
There's one per direction, right? Because it's unit.
and Z is I. Exactly. So this is x plus IY. So any vector in the unit tangent bundle to x plus IY has length YI and some angle. What's the angle?
Right.
Whatever
And
you
then
want it to
this Theta doesn't appear anywhere else, so it is actually independent.
Exactly.
Okay.
Exactly. That was the point. So this stabilizer, what it's actually doing is giving you that last degree of freedom to move the unit tangent vector.
Very aesthetically pleasing.
It indeed is. Indeed it is. Right. What did I want to say? So we proved transitivity. Now, what about that it's a free action? There's no, that it's a, proper or whatever.
Stabilizer.
Yeah, the stabilizer being trivial.
Making me wonder, is there more mileage you can get studying SL2Z just by, or maybe GL2Z just by, or GL2K or GLK, just by finding more decompositions of it? This is like a lot of mileage out of the NAK decomposition.
Other decompositions
A lot of
are,
mileage out of KAK. I've seen a lot of mileage out of Bruja.
uh-huh. There's all kinds of,
Other decompositions we just haven't found yet that we don't realize would give us all sorts of great.
so in terms of one parameter subgroups of G, there are lots of decompositions. So the one parameter subgroups of G, one parameter subgroups are either something that's an N or something that's an A or something that's a K. They're either diagonalizable.
What do you mean by one parameter?
So in other words, something that depends on a single, like N depends on,
Oh.
there's
okay,
one
okay.
parameter here, as opposed to G, which is
Yeah, so like one-dimensional
one-dimensional subgroups.
subgroups.
Yeah.
Okay, okay.
Yeah, so either you have a unipotent, you have something that's diagonalizable over R, or you have something that's diagonalizable over C. Right, this cosine theta is diagonalizable to e to the EI theta, E minus I theta.
Okay. But then there are two parameter subgroups that are not products of the.
There are two parameter subgroups that are not,
Like star 0 1.
Star star 0, 1 is NA. That's the Borel.
Or is it even possible to have them not be? That's a good question.
So in terms of parameterizations by single variables that are moving, these are the only ones. Now, that means you could have an AAA decomposition if you wanted to. Okay, what would that look like?
Is it actually possible?
Sure. At least locally.
Right.
So what is an AAA decomposition? You start with I up, you get to flow by some A. So different conjugations of A. You get to flow by some A, which means maybe we can move to here. Then you get to flow by another A, but you could flow by an A by conjugating A, meaning like rotating. Let's say you rotate 90 degrees. Then you flow by A, and then you unrotate 90 degrees. So that would be a second A. And then you could do another A, which is, rotate by 45 degrees or something and flow by another geodesic and unrotate by 45 degrees. So.
But would these be fixed conjugations?
Yes.
Of A? Okay.
Yes. So you could do 3 A's. You can't do 3 K's. Is that true? You can't do 3 K's? Maybe you can actually. No, I think you can do 3 K's. So here's how you would do 3 K's. The first K should be something that's fixing every K fixes a point, right? Every A fixes 2 points on the boundary. Every K fixes 2 points. One of them is in the upper half plane, one's in the lower half plane. And every N fixes the point at infinity twice. Right? All of these are classified by their fixed points. They all have, what does it mean to be a fixed point? GZ is equal to Z. Well, because this is AZ plus B over CZ plus D is equal to Z, you get a quadratic. You multiply this over here, you get a quadratic.
Right.
So they're going to have 2 fixed points. The question is, are those 2 fixed points complex? In which case it really has 1 fixed point in the upper half plane, that would be K. Are they real and different? Then you get A. Or are they real and the same? Which is N. Okay, so that's the distinction between the 3. So if you want to do KKK decomposition, then you choose 1 point, you rotate with respect to that point somewhere. Then you choose another point, and you're sort of swinging from trees or something. And you rotate with respect to that point somewhere, and then you have a third point, could be I for all I know, and then you rotate with respect to that point, and you can reach at least locally, you can reach anything through 3 triple K decompositions. So
the only thing is, it might be a bit nasty to think about it that way, right? Like in the triple A case, right? You're sort of like, you keep moving the points around with each copy, right? That's
Sure.
hard to visualize, right?
Not necessarily. You get used to it. I mean, what's an NNK decomposition, right? Again, you can do this all day. But so there's 3. So the number of decompositions, let's just write them out. There's 3 choices for N, 3 choices for A, 3 choices K. There's 3 cubed. Okay, there's 27 decompositions.
Combinatorial numbers here.
Right. Go to town. They each have a geometric description like this. Some will be more useful for depending on which problem you're solving. And indeed, there are lots of certainly NAK is somehow the most classical, but there are lots of examples in my own work where an AAK decomposition was needed.
Really?
Yeah.
Oh.
What people there's usually a good reason to have a K at the end, which we'll maybe talk about when we talk about sort of restricting representation to a maximal compact. That has there's a very good reason to do that. But then there's usually one parameter that's sort of responsible for some growth, and A is doing that in rank 1 groups.
And you do it naturally, I suppose, right? Like in the context of the problem.
Exactly. And then so what you'll see people write is an HAK decomposition, where H can be either K or A or N depending on the context. Okay, so this is kind of something that really appears in a lot of examples.
Interesting.
All right. So why is the action transitive? We saw that it's transitive. Why is the stabilizer? What's the stabilizer of I up is trivial? Well, we already know the stabilizer of I is cosine is K. But I want this K to be 0. In other words, I want e to the 2I theta to be 1, which means theta is either 0 or pi, but theta being pi is plus or minus 1, which is exactly what, so this stabilizer is trivial. In PSL2, the stabilizer is trivial. When theta is equal to pi, then I get here minus 1, 0, 0, minus 1. Okay, so the stabilizer is trivial for PSL if G is P. Now I really need to emphasize PSL2.
Because otherwise you could get the other variant, right? The counter diagonal
Well, yeah,
matrix.
no. All I mean by this P is that otherwise the stabilizer is plus or minus 1. In other words, if you want SL2R, then you have to do SL2R minus.
I mean, there are 2 rotations that would do it.
Exactly, 2 rotations that do the same thing.
Right, exactly.
Exactly because of this 2. Okay. Or if you're like the group K is really the group K mod plus or minus 1, which means K really only goes from 0 to pi instead of 0 all the way to 2 pi.
Hey, why don't we see it that way? I guess like PSL2, I mean, this is.
We absolutely,
You have to mod out by something at some point.
yes.
Yeah.
Yeah, just notice that plus or minus 1 is a subgroup of K.
Okay, so that's like the, let's say, proper NAK for PSL is sort of like K modded out by,
Plus or minus.
right, that matrix.
Okay, good. So we see this under this identification. This is the last thing I wanted to say. Well, I wanted to say a lot more, but we'll go at any pace. Is this Gelfand reinterpretation of the geodesic flow as being a diagonal flow on G. So let me say that again. So Gelfand, under this identification, Gelfand realizes that the geodesic flow acting on the unitangent bundle is exactly the same as the right regular action of AT. AT is e to the t over 2, e to the minus t over 2, which is the exponential of the t times 1 negative 1. This is an element of the Lie algebra. Have we talked about Lie theory? I can't remember. No, okay. All right, I'll just leave that there. Never mind. The right regular action of this on G itself. So under this identification. Okay, why is that true?
Another thing that's confused me a lot is how do we choose actions to be left or right? Right, so it's like when you're taking geodesic flow, the left one, why is this a left action?
So in other words, why isn't it? So on the left, we move things by, well, in number theory, on the left, we move things by discrete groups. And on the right, we act by continuous groups. In other words,
the choice we're making here.
This is a choice we're making in this identification and in the way that we write things. In other words,
like mirror everything and like the theory would still.
We could mirror everything if we change the meaning of action. In other words, if I have GI, and then I say, well, I want to act, I have some representation, I want to act by an element H. What should that action be? Is it H times G, or is it G times H? So that's where I'm saying it needs to be a right regular action.
G times H.
Yeah, so that this representation gives me G times H. And what does that do to I?
Because I understand that we're going to want some sort of compatibility, right? Like having, if you have on opposite sides, then you don't have to worry. Okay, wait, so you said left was discrete?
Yes, we act by the discrete group on the left of G, and we flow on the right.
Right, the flowing is certainly not discrete, right?
right?
And then on the left,
You can define the action the other way, but what it does to I and what it does to I up, it has to be, it is the right action that does the geodesic flow.
then in this example, the left will be what? PSL with Z?
The left will be the action of SL2Z. Yeah, exactly.
Okay. That's how we have a discrete continuance.
Well, the fact that, I mean, you could also act on the left. It just won't be doing what you, it won't be doing what you might think it's doing.
Okay.
In other words, if you act on the left by K,
Right.
for example, what does that do? So this is a good exercise.
So can't you
Since
do
I'm
like
ahead of time.
KN or something like that? And then,
You can, and people do. It's just that so if you put K on the left, it does not stabilize I up because it stabilizes, depends on which K it is. Whatever you have in between, it may or may not stabilize. And in fact, this K, a K here will rotate not about I up, but about whatever this point is.
right.
So anyway, let's just quickly see this and then I have to let you go. Why is this the case? Well, okay, so let's start with I up, here we are. I'm acting, so what's the matrix that I act by is AT. We know what AT does to I up, it moves it over here.
Right. This
And now I act by G, which is NAK. K rotates this, A flows. I'm showing you that A flows, and then N rotates it again. In the interest of time, no, I should really do this one computation. We'll do this sort of more slowly next time. Start here, but let me leave you an exercise, which is I'm realizing I skipped earlier on when we saw the distance. So what is the distance? The distance between 2 points Z and W in hyperbolic space is equal to, a better way of writing this is that the hyperbolic sine, hyperbolic sine of D over 2 is equal to U of ZW over 2, where U of ZW, there's a very, a function that arises in all kinds of applications, so it's good to have a separate name for it, is the Euclidean distance between Z and W divided by, do I put a 2 here or not? I do put a 2 here for various reasons that we'll discuss last time. Imaginary part of Z, imaginary part of W.
Wait, so here we're saying, wait, that D is that Euclidean?
No,
Or
this is
that-
the hyperbolic distance.
Okay, so you have hyperbolic sine of the hyperbolic distance of
Yes.
2, and then you're saying it's giving you
So I'm saying
Euclidean on top.
Euclidean distance,
and on the
divided by
bottom,
this.
okay.
okay? And a hint is that U itself is distance invariant.
The hint is that
Hint is that U of GZ, GW is U of ZW. Well, as it must be.
yeah, it doesn't must.
Bless you. So this is easy to show. You just write GZ minus GW. Anyway, I'm doing the algebra for you. Do a little bit of algebra and you'll see that the imaginary parts here, which each have a CZ plus D and a CW plus D norm squared, exactly cancel
Right.
this difference. And once you see that, then it's a matter of determining whether this formula is true for Z being I and W being YI.
So why do we want this formula?
Oh, just to know exactly what the distance between 2 points is.
We know exactly the arc sine.
Yeah, it's arcs, exactly. It's arc sine of,
Exactly.
I mean, like the hyperbolic, the inverse hyperbolic functions are just quadratics, right?
yeah, they're
So
logs,
then-
yeah. Hyperbolic sine is a very simple function, right? It's e to the x plus minus e to the minus x over 2. Right, this is a very simple function. If we want to do hyperbolic geometry, we're going to see a lot of these kinds of functions.
Right, because the thing is that I remember the first time I looked up this hyperbolic stuff, the first thing my brain went to was, oh, what is explicit, like, like metric,
Yes,
right? And then you see this nasty, right, like sort of like,
the distant function is very
right, like long and like, and I'm like, well, right? Then clearly this wasn't how they came up with it, right? Like you don't just write that down like. your
That's
first
right.
thought,
That's right. This is all consequence of the action. That once you decide you're going to act as a linear transformation on projective space, you're forced into fractional linear action. Once you say, okay, what's the geometry that allows that fractional linear transformation to be an isometry, you're forced into the Riemannian structure, dx squared plus dy squared over y squared.
So that's how this was born.
That's how this was all figured out. Yep.
Mm.
And then Gelfand says, actually, you can see all of this geometry that we're doing is just algebra. It's just multiplying matrices,
It's spectacular, right?
which is spectacular, yeah, and very powerful.